In this first outcome, we turn to dynamics, the study of why things move. We'll link work, power, and efficiency to energy, use momentum to make sense of collisions, and finish with objects going round in circles at a steady speed. Let's make a start. So, what's the plan for this outcome? Dynamics is all about why objects move, and we'll get there through forces and energy. First, we connect the work done by a force to power and efficiency. Then we bring in momentum to analyze collisions in a straight line. And finally, we describe steady circular motion using angular speed and the centripetal force. And throughout, every idea is pinned down with a worked calculation in proper SI units. Before we dive in, let's fix a few words we'll lean on. Work done is the energy transferred when a force moves its point of application, and it's measured in joules. Energy is simply the capacity to do work, also in joules. Power is the rate of doing that work, or transferring that energy, measured in watts, where 1 watt is 1 joule per second. And efficiency is the fraction of the energy you put in that comes out as something useful, usually written as a percentage. Let's start with work done. A force does work when it moves an object along its own line of action. And for a force acting straight along the displacement, work equals force times distance. Force is in newtons, distance in meters, and the work comes out in joules, where 1 joule is the work done when 1 newton shifts something 1 meter. Two things worth remembering. If nothing moves, no work is done, no matter how hard you push, and work is a scalar, so it has size but no direction. Very often, though, a force doesn't line up neatly with the motion. Picture pulling something with a rope held at an angle, call that angle theta. Only the part of the force along the direction of travel actually does work, so we use work equals force times distance times the cosine of theta. If theta is 0 degrees, the cosine is 1, and you get the maximum work, force times distance. But if theta is 90 degrees, the cosine is 0, and no work is done at all, which is exactly why a perpendicular force, like the tension in circular motion, does no work. Let's put that to work with an example. A child pulls a sledge with a rope at 30 degrees to the ground using a force of 50 newtons, and the sledge slides 8 meters along the flat. So our force is 50 newtons, the distance is 8 meters, and theta is 30 degrees. Using work equals force times distance times the cosine of theta, we get 50 times 8 times the cosine of 30 degrees. The cosine of 30 degrees is about 0.866, so that's 400 times 0.866, which comes to roughly 346 joules of work done on the sledge. Now to power, which tells us how quickly energy is being transferred. Power equals the work done divided by the time taken, and its unit is the watt, where 1 watt is 1 joule every second. There's also a handy version for steady motion. Power equals force times velocity. The key idea is that a more powerful machine gets the same job done in less time. Here's power in action. A motor lifts a 20-kilogram load through a height of 15 meters in 10 seconds and will take G as 9.81 meters per second squared. The useful work done is the gain in gravitational potential energy, mass times G times height, so that's 20 times 9.81 times 15, which is 2,943 joules. Divide that by the 10 seconds, keeping our units as joules over seconds, and we get a useful output power of about 294 watts. Real machines never manage to turn all their input energy into something useful. Some always leaks away as heat and sound. Efficiency captures this. It's the useful energy transfer divided by the total energy input times 100 to make a percentage. You can write it with powers just as easily. Useful power out over power in. Efficiency is always below 100% and has no units, and reducing friction and resistance is how you nudge it higher. Do note, energy is still conserved. The so-called lost energy simply isn't useful to us. Let's put a figure on it. An electric motor is fed 5,000 joules of electrical energy and does 3,500 joules of useful work lifting a load. Efficiency is the useful energy over the input energy, times 100. So 3,500 divided by 5,000 times 100. That's 0.7 times 100, giving 70%. The other 1,500 joules is wasted, mostly as heat. Now we switch to momentum, which you can think of as the quantity of motion an object carries. Linear momentum is mass times velocity, and its unit is the kilogram meter per second. Crucially, momentum is a vector, so direction matters in a collision. A heavy, fast-moving object has a large momentum and is correspondingly hard to stop. This leads us to Newton's second law in its fuller form. Force equals the change in momentum divided by the change in time. In other words, force is the rate at which momentum changes. When the mass stays constant, this boils down to the familiar force equals mass times acceleration. A bigger force changes momentum faster, and turning that round, spreading a given change over more time, reduces the force, which is precisely how crumple zones protect you in a crash. The units check out too. Kilogram meters per second, divided by seconds, gives newtons. Closely related is impulse, which is force times time measured in Newton seconds. Impulse equals the change in momentum, so force times the time interval gives you the change in momentum. On a force against time graph, the impulse is simply the area underneath, and for a force that varies, finding that area is how you get the impulse. This is the reason a longer contact time softens a blow. And note 1 Newton second is numerically the same as 1 kilogram meter per second. Let's read an impulse straight off a graph. A ball is struck by a bat, and the force rises, then falls, tracing out a triangle on the force against time graph, peaking at 600 newtons over a contact time of 0.10 seconds. The impulse is the area under that graph, and since the shape is a triangle, the area is a half times the base times the height. So that's a half times 0.10 seconds times 600 newtons, which is a half of 60, giving 30 newton seconds. And that means the change in momentum is 30 kilogram meters per second. One of the most useful principles in all of mechanics is the conservation of momentum. In an isolated system, one with no external resultant force acting, the total momentum stays exactly the same. So the total momentum before a collision equals the total momentum afterwards. Because momentum is a vector, you pick a positive direction at the start and stick to it religiously. This principle lets us solve for an unknown velocity, and beautifully, it holds for every collision, elastic or inelastic alike. It's worth separating two types of collision. In an elastic collision, kinetic energy is conserved as well as momentum. The objects bounce cleanly apart rather than sticking, and hard snooker balls are the classic near example, though truly elastic collisions are rare in daily life. In an inelastic collision, momentum is still conserved, but kinetic energy is not. Some of it turns into heat, sound, and deformation. In the perfectly inelastic case, the objects stick together and move off as one, like two railway trucks coupling up. Let's work through a perfectly inelastic collision. a 1,500 kilogram car, moving at 20 meters per second, runs into a stationary 1,000 kilogram car, and they lock together. Take the direction of motion as positive. The momentum before is 1,500 times 20, plus 1,000 times 0, which is 30,000 kilogram meters per second. Afterwards, they move together with a combined mass of 2,500 kilograms at some velocity v, conserving momentum. 30,000 equals 2,500 times v, so v is 30,000 divided by 2,500, which is 12 meters per second in the original direction. Here's one where only one object is unknown. A 2-kilogram trolley moving at 3 meters per second strikes a stationary 1-kilogram trolley, and after the collision, the 2-kilogram trolley carries on at 1 meter per second in the same direction. The momentum before is 2 times 3 plus 1 times 0, which is 6 kilogram meters per second. The momentum after is 2 times 1 plus 1 times v, that's 2 plus v. Conserving momentum, 6 equals 2 plus v, so v is 6 minus 2, which is 4. The 1-kilogram trolley moves off at 4 meters per second. Let's pause and check a few things. First, why does a force acting at 90 degrees to the motion do no work at all? Second, can you state the difference between work and power and give the units of each? Third, which quantity is always conserved in any collision, whatever its type? And fourth, in an inelastic collision, where does the lost kinetic energy actually go? Have a think before we press on. Now we turn to circular motion. And first, we need the right unit for angles, the radian. The radian is the natural way to measure an angle. 1 radian is the angle at which the arc length equals the radius. A full circle is 2 pi radians, which is 360 degrees, so pi radians is 180 degrees, and pi over 2 radians is 90 degrees. The arc length is just the radius times the angle in radians, and using radians is what keeps our circular motion equations simple and tidy. Consider an object going round at a constant speed. Its speed is steady, but its direction is forever changing. The period is the time for one full revolution in seconds, and the frequency, the number of revolutions per second, is 1 over the period, measured in hertz. The angular speed, written omega, is 2 pi over the period, or 2 pi times the frequency in radians per second. Linear speed and angular speed are linked by v equals omega times r. And here's the subtle point. Because the velocity keeps changing direction, the object is genuinely accelerating even at constant speed. That acceleration always points inwards, towards the center of the circle, and we call it centripetal acceleration. It equals v squared over r, which is the same as omega squared times r. Since there's an acceleration, there must be a resultant force causing it, the centripetal force equal to mass times v squared over r, or mass times omega squared times r, and it too points to the center. That force can be provided by tension, by friction, or by gravity, and if you remove it, the object simply flies off along a tangent. Let's put numbers on a turntable. An object sits half a meter from the center of a turntable that completes 1 revolution every 2 seconds, and we want the frequency, the angular speed, and the linear speed. The frequency is 1 over the period, 1 divided by 2, which is 0.5 hertz. The angular speed is 2 pi over the period, 2 pi divided by 2, which is pi radians per second, about 3.14 radians per second. The linear speed is omega times r, 3.14 times 0.5, so about 1.57 meters per second. Now, a car going round a bend. A 1,000 kilogram car travels at 15 meters per second around a bend of radius 50 meters, and we want the centripetal acceleration and force. The acceleration is v squared over r. That's 15 squared over 50, which is 225 over 50, giving 4.5 meters per second squared. The centripetal force is mass times that acceleration, 1,000 times 4.5, which is 4,500 newtons, and here it's supplied by the friction between the tires and the road. Let's do one using angular speed directly. A 0.20 kilogram ball on a string is whirled in a horizontal circle of radius 0.80 meters with an angular speed of 5.0 radians per second, and we want the acceleration and the tension. Using acceleration equals omega squared times r. That's 5.0 squared times 0.80, which is 25 times 0.8, giving 20 meters per second squared. The tension provides the centripetal force, so it's mass times acceleration, 0.20 times 20, which is 4.0 newtons directed towards the center. Circular motion attracts a few stubborn misconceptions, so let's clear them up. People say there's an outward centrifugal force, but the real force actually acts inwards, towards the center. They say constant speed means no acceleration, yet the direction is changing, so there most certainly is an acceleration. They say the centripetal force does work, but it's perpendicular to the motion, so the work it does is zero. And they imagine that if the string snaps, the ball flies straight outward, when in fact it heads off along the tangent, not radially outward. Let's gather the key terms from this second half. Momentum is mass times velocity in kilogram meters per second. Impulse is force times time, and it equals the change in momentum measured in Newton seconds. Angular speed, omega, is the rate of change of angle, equal to 2 pi over the period in radians per second. And the centripetal force is the inward resultant force that keeps an object moving in a circle, equal to mass times v squared over r. One more round of questions to test yourself. How many radians are there in a complete circle? Can you write down 2 different equations for the centripetal acceleration? In which direction does the centripetal force always point? And if you swing a stone on a string faster and faster, what happens to the tension you need? Take a moment with those before you move on.